A familiar star burns in the heavens. Its light fuels the engine of life. Our planet luxuriates in its warmth. We are all children of the stars, growing up under the golden gaze of our nearest and most precious star, the sun. But where did this benevolent giant come from? And what will be its fate? The sun that moves through our skies appears to be the most dependable aspect of our universe. An amber disk rising without fail day after day. But the sun has a long and turbulent past. Its future too will be violent and spectacular. This is the story of our sun, from Genesis to extinction. Understanding the sun's life cycle requires time. You can't watch a tree for 5 minutes and discover how trees grow. But look to the night skies. It's a forest, stars in all stages of growth. Here are the solar seeds, shoots, saplings, and decayed wood. Together, they tell the 10 billion year life story of our sun. It's a biography that can be read by the Hubble Space Telescope. With its amazing close-ups, it pieces together our sun's story by showing us other stars during birth, growth, and death. Poised 380 miles above the Earth, Hubble views the heavens, our eye to the sky, an eye with 20/20 vision.
Looking at the stars from the ground is like looking up through the bottom of a swimming pool, where everything is smeary and distorted. That's why stars twinkle at night. Once we get into space, we have an exquisite clarity. That allows us to see things that are 10 times clearer than you can ever see from the ground.
The earthbound view blurs. But in orbit, Hubble's eye zooms into the distance. And then zooms again through a peephole in our galaxy to other galaxies so distant that the journey of light takes 10 billion years. But Hubble doesn't need to see that far to relate the opening chapter in our sun's life. The Space Telescope turns and sees Eta Carina, a titanic superstar. The violent furnace at its core is a fantastic nuclear reactor. Being fused in this crucible of creation are the elements needed for life. But it is a star on the verge of self-destruction. The two massive clouds of dust presage the blockbuster that is to come. Eta Carina will soon end its years as a supernova. In the giant detonation, small atoms are thrust together to make larger, more exotic atoms. Only here does the cosmic touchstone create the precious metals gold and platinum. No wizard who ever waved his wand could have brewed such alchemy. Blasted out, this gas and stardust can form fabulous clouds called nebulae, here taking the shape of a crab. More debris, but here blown across the heavens by the blast from supernova, draping the sky as the Veil Nebula. In contrast is the vast Eagle Nebula, where time and stellar wind are sculpting cosmic debris into great columns. our entire solar system would be less than a pinhead against these enormous clouds, pillars of creation seen by Hubble. Billions of years ago, ingredients like these were part of the fantastic brew that came to be our own precious solar system. On Earth, blast waves destroy all in their path. But in space, they can be waves of Genesis. Over 6 billion years ago, the blast from a supernova crashed through a cloud of dust and gas. This dying breath was the kiss of life for a new star. The dust is concentrated by ripples of galactic shock. Gravity pulls in still more material. Heat and pressure at the core become intense. A nuclear reactor fires up, and jets of gas shoot out. Real starbirth seen by Hubble. Telltale jets of a tearaway infant star.
Our sun was like this, and we've seen for the first time the environments around stars that are forming. And we've seen it on the scale of our own planetary system, and we've seen what we long suspected would be there.
Jets heralded the dawn for our sun 5 billion years ago. Around it swirls a disk of gas, dust, and rock. It's a cosmic soup slowly being stirred. The gravity of the central star pulls upon this maelstrom. Heavier elements such as metals stay near the center, while the lighter elements, hydrogen and helium, escape to the outer regions. This separation will give the planets that they are forming their different characteristics. Our solar system at its birth. Reality or speculation?
The nearest place to find out is in the Orion Nebula. We think that's a region where stars are forming like our sun right now.
A stellar nursery where regions of dust and gas are collapsing, compressing, and then kindling the nuclear fire of starbirth. Hubble sees into the Orion with amazing clarity. Look closely and see a star. Although burning bright, it's almost obscured by the disk of dust that swirls around it.
Now with the Hubble pictures, you can see that there are disks there which are about the size of our own solar system and might indeed form solar systems like ours.
Over 4.5 billion years ago, around our own sun, spun a frisbee of rocks and dust, rotating in the same direction, waltzing to the same tune. But the dance was not at all serene. Fragments collided and coalesced. Out of the debris slowly grew the sun's family. With so much material flying around, it wasn't always easy to survive. Young planets were struck. Some were annihilated, others reformed. As embryo planets grew, their gravity increased, attracting even more material. A few large planets formed, some big enough to have their own entourage of debris. This complex swirl of activity eventually settled down, and around the central star promenaded a few new planets. Their gravity drew in the remaining debris, and they continued to add mass. Finally, it was possible to make out just a handful of planets circling a star. But the star was having growing pains. From deep within, the nuclear inferno raged, forcing the young sun to expand. But gravity pulled the star back in. It was like a giant tug of war. After a billion years, the sun reached equilibrium. and slung in the harness of its gravity are the young planets. Our solar system had been born. But are we living in a unique system? Possibly not. Perhaps in the corner of some galaxy there exists the exotic children of some other star. Hubble has started to look. It sees another star with a disk of swirling dust called Beta Pictoris.
The discovery we made around Beta Pictoris is that it's surrounded by a disk of material. And the exciting thing about this is the configuration of the material that we saw, the shape of it, is actually in a flattened disk, as if it were a phonograph record with a star at the very center. But there's a clearing of material, and that clearing is about the size of our own solar system. And the indication there may be that the clearing is caused by the formation of planets.
So far, no planets have been detected around Beta Pictoris.
Planets are extremely hard to see directly. If you can imagine trying to read the inscription on a flashbulb as it goes off in your face, a planet is about 1 billion times fainter than the parent star, and it's right next to it.
The Lick telescope also hunts for planets, but it does so by looking at stars.
We can't see the planets directly orbiting other stars, but what we can do is watch the response of the star due to the gravitational pull by the planet. And we watch to see the star wobble in space due to the presence of the planet.
Like a hammer thrower pulled out by the weight of the hammer, he wobbles as he spins.
This is the most beautiful velocity curve in the history of astronomy. It really is.
Look at the postfix.
Jeff Marcy and Paul Butler are looking at a star. If it's moving in a circle, then its velocity will continually change in a repeating sequence, like a sine wave.
And this last point we just got last night, that is so beautiful.
That's beautiful.
And the points all sit right on a sine wave, showing that the star wobbles in a perfectly sinusoidal pattern, meaning the star is going in a circle, and hence the planet is going in a circle. So
this point here is almost like the first night we ever took data.
And we've been following this star for 10 years. This may well be the first bona fide solar system-like planet ever found. It's basically like Jupiter.
Searching for planets like those in our solar system is the frontier of current research. There's so much to be discovered. Maybe it will turn out that our solar system is not unique. But even if it isn't, the parade of planets that circles our sun is still an exotic group. And it seems to fall into a very neat pattern.
The solar system has kind of an organization. Close in toward the sun are the terrestrial planets, the planets that are made of rocks and silicates, like the Earth. Further away are the gas giants, mostly made of hydrogen, a lot of water, helium, contain a lot of gas and a lot of material. And furthest away are the icy dwarfs, things like Pluto.
Hitch a ride as we tour the sun's dominion. See the sunrise on far-off worlds. First stop, Mercury, the sun's nearest neighbor, possibly rich in gold and platinum, heavy elements that stayed near the sun. But Hubble will never look at these riches.
Ironically, even though Mercury is one of the closest objects to us in space, we need to avoid it. If we made a mistake and actually peered into the sun, the telescope would get quite hot with all that sunlight coming into it. In a sense, we'd have a meltdown on the telescope. We'd quickly be out of business.
But the sun won't damage radio telescopes. Radio maps and images from the Mariner 10 spacecraft can help us paint a picture of Mercury. Its scarred face tells of duels with comets and asteroids. We see a small, bleak world where gravity is too weak to hold on to an atmosphere. With no blanket to insulate it, Mercury is a planet of temperature extremes. At minus 300 degrees Fahrenheit, the nights are cold beyond imagination. From freezer to furnace. because the touch of sunlight heralds a day that will see temperatures soar to 800 degrees Fahrenheit. Life here wouldn't stand a chance. Picture this. Worlds farther from the Sun, like Earth and Venus, were better suited for germinating the seeds of life. Ellen Stofan knows both these planets.
Earth and Venus are often thought of as the twins of the inner solar system. The two planets are about the same size and they're made of about the same material, and that means, or at least you would think that that would mean, that the two planets had evolved in a similar way and would have very similar surfaces now. But in fact they didn't at all. At some point in their history, probably several billion years ago, the two planets diverged.
Earth with water and oxygen. It's an exquisite balance of land, sea, air, and life. While Venus is a dead, suffocating super greenhouse. Today the two planets are hell and high water. One difference is their direction of spin.
The Earth has what's called prograde revolution. It spins in this way. On Venus, however, it's retrograde. It spins from an Earth perspective backwards. Now, why is that? Some people think that very early in the history of Venus that the body was hit and caused it to start rotating backwards. There's actually an alternate theory which says it's not really violating any laws by spinning backwards, and we just could have this sort of Earth-centric view that says everybody should spin the same way we do.
Only recently have we learned the secrets of Venus. It hides behind thick clouds. We only saw behind the veil when the Soviet Venera craft glided through. Venera fell through clouds of sulfuric acid into a scorching, hostile world with crushing atmospheric pressure. Venus has a parched, rocky surface, born from ancient volcanism, remnants of old lava flows, now broken into boulders. A later visit by the Magellan craft sent back information to build these images. Flow upon flow of lava has split from volcanic peaks. These have run for hundreds of miles across the plains. There are mountains, ridges, and valleys of ancient volcanoes building up layer cake mountains of lava cut by ridges and valleys. Venus had a violent past. So did the Earth. 4 billion years ago, it would have been hard to tell which planet this was. Each ran red with lava. Long ago, these two worlds were not too different.
Venus and the Earth both started out with about the same amount of carbon and oxygen, but on Venus, that carbon dioxide is all in the atmosphere. On the Earth, we probably started out with a lot of carbon dioxide in the atmosphere, but it was fixed into rocks by life, by little organisms that took that carbon dioxide out of the atmosphere and put it into things like their skeletons. That's now formed limestone rocks, like you see here behind me.
Carbon dioxide, a greenhouse gas, remained in Venus's warming atmosphere. Water vaporized, adding to the greenhouse effect. 100, 200, 300 degrees Fahrenheit. Venus was on a one-way street to hell. Today, it's 800 degrees Fahrenheit.
If you landed on Venus, you'd be killed in seconds by either the heat or the extremely high pressure that is produced by this thick layer of clouds.
Earth. For over 3 billion years, it's been just the right temperature to hold on to the cornerstone of life. Water. It runs through land, sea, and air. This hydrocycle is the secret of the planet's success. Water dissolves and transports the chemicals required by all living creatures.
My favorite object really has to be the Earth. The Earth is a fantastic world, continents, oceans, teeming with life. The Earth has evolved its own chemistry to the point where it's actually conscious and aware of itself. That's got to be a winner in the solar system.
Mars, also a blue planet with oceans, but long, long ago.
The conditions on Mars 4 billion years ago were very similar to the conditions on Earth 4 billion years ago. But 4 billion years ago is when life arose on Earth. Could life have arisen on Mars at the same time?
We once thought it could. Turn-of-the-century maps of Mars feature lines, described by an Italian astronomer as canali.
A set of single and double straight lines that speak persuasively of intelligent origin. The only question is, which side of the telescope was the intelligence on? And the answer is clearly it was on our side of the telescope.
Today, there's no chance of intelligent life because long ago, Mars lost most of its atmosphere and became a freeze-dried world. Mars today. Coming from nowhere, spectacular dust storms race over the barren desert. To find water, look down, and you'll probably discover plenty, frozen beneath the surface. Or as ice at the top of the Martian world. White poles cap a russet planet caught in Hubble's eye. Our Earth and Moon crest the horizon. Stay and watch the sunrise on this desolate world. Venus shines, the start of another day. Stand on the last of the rocky planets and see dawn break. Another one for the album. Beyond Mars lies the asteroid belt, a broad sash of fragments. They were prevented from joining together by the gravity of their giant neighbor, Jupiter. When the planets were forming, Jupiter went on a planetary binge. Its increasing gravity gorged on ever more gas and dust. It just grew and grew. Just 10 times larger, and Jupiter might have fired up as a star. Jupiter marks the start of the gas giants. Jupiter's rings, a shimmering sash of talcum-fine particles that glide across its vast girth. From the cloud tops, all seems serene. But look down. The most magnificent storm in the solar system, the Great Red Spot. A helter-skelter of wind swirling at hundreds of miles per hour. It's over 15,000 miles across. High above the storms, the sun disappears behind Io, one of Jupiter's 16 moons. Sulfur volcanoes erupting against the darkness. Parading around Jupiter and Saturn are hosts of strange moons. Jupiter's Europa, where a frozen icy surface may cover warmer oceans. And Jupiter's largest moon, Ganymede, with its cratered, wrinkled, and furrowed surface heaved by ice quakes. Other moons with smooth surfaces, like Saturn's Mimas, a moon beaten but not broken by some ancient smash. And Jupiter's Callisto, battered by cosmic ballistics. Titan, one of Saturn's 18 moons. Primitive gases give it its strange hue. A tangerine world with marmalade skies. Its atmosphere is like that of primitive Earth, but in deep freeze. Those lakes are liquid methane. Saturn's moons, the forgotten players, for it's the rings that steal the show. Although they could stretch from Earth most of the way to our moon, they are exquisitely thin. Icy pearls strung around the planet. The largest are only 10 yards across. A view of them from Saturn's cloud tops. In Bath, England, William Herschel discovered a new planet. As well as being an astronomer, he was also a composer, and he'd invite King George III for evenings of music and astronomy.
There are many stories told about the relationship between Herschel and the king, including the fact that Herschel would invite the king often to his gardens to view heavenly objects, even when it was cloudy, and he did this by having the equivalent of slides or lantern slides placed in little illuminated boxes to which he would turn his telescope so that the royal party, no matter what the weather, would always see something celestial.
Herschel discovered a new planet. Wishing to curry favor, he tried to name it George's star after the king. But the idea didn't go down too well with other astronomers, and the new planet was dubbed Uranus instead. Like Saturn, it has rings, less impressive in appearance, but more spectacular in formation. Rings formed after impact. The planet was struck by a massive body and teetered on the brink of oblivion. Gravity won, and the planet pulled itself back together. Rocked over on its side, the lasting memory of this near catastrophe is a wisp of fine, dark rings around its equator. Rings captured by the Hubble Space Telescope. They appear to change from darkness to light as they glint in the rising sun. Uranus's moon, Miranda.
I think the most exotic place in the solar system is probably Miranda, which is a small moon of one of the outer planets, and it looks like it's ice, and it's been deformed in these amazing ways so that it has these gigantic mountains and canyons and abrupt left turns in its mountains, and it is really weird. It has such massive features that I think it's exotic as anything you're going to find. So it's probably the oddest place in the solar system.
Robot explorers are the only way to discover the secrets of the outer planets. Voyager 2, 1989, passing Neptune.
When Voyager flew by Neptune in 1989, the biggest feature on Neptune was a huge dark spot in the southern hemisphere.
Neptune has the fastest winds in the solar system, blowing at up to 1,000 miles per hour. 5 years after Voyager, Hubble went looking for these tornadoes.
When Hubble turned its cameras towards Neptune in 1994, it took many pictures of Neptune. Each one of these little blocks is a map of Neptune.
The results surprised Heidi Hammel's team.
Voyager's great dark spot would have been down here in the south. In fact, that feature had disappeared. Now, that doesn't mean that Neptune didn't have dark spots. we discovered that up in Neptune's northern hemisphere, there was a very large dark spot, similar in size and shape and contrast to the spot that Voyager had seen. But it was in the opposite hemisphere. Those spots couldn't have moved across Neptune's equator. The winds of Neptune would have torn a spot apart if it had tried to do that. So Neptune had really changed its spots dramatically in just 5 years.
Neptune, ringed with dark, icy fragments. Pass through them and find Neptune's moon, Triton. This is the coldest body in the solar system. Liquid nitrogen is locked beneath the surface, but it bursts through and turns to snow. Blown downwind, the trails glint in the rising sun. Beyond Neptune in outer space lay Planet X, predicted but unseen. In 1930, a young Kansas farm boy, Clyde Tombaugh, was working at the Lowell Observatory in Flagstaff, Arizona. As the sun went down, he would look up. Evening saw him turn his hopes to the heavens in search of the invisible planet. For more than a year, Tombaugh exposed photographic plates to the pale polka dot light of the night sky. He was hoping the faintest glimmer from Planet X was finding its way onto just some of the hundreds of photographic plates he'd made.
Clyde knew exactly what he was looking for. He was looking at 2 photographic plates of the same area of sky, looking for an object that would be shifting its position by a certain amount.
When he wasn't photographing, Clyde spent his life staring into a blink comparator, rapidly switching between views of 2 plates exposed 2 days apart. He was seeking a tiny object that changed position against the starry background.
And he had a mental note in his brain: if I find something that is shifting from one plate to the other by this particular amount, then I know I have my planet that is beyond the orbit of Neptune. And then, like a dream, he sees the object, and he sees it shifting. And he says, "That's it." Clyde knew what he had discovered within 2 seconds of his find, but he had to confirm it. He had to make tests. And Clyde says, for 45 minutes I was the only person on Earth that knew of the existence of Pluto, and it was incredible.
It is a discovery by traditional astronomical methods made in this century of a new planet. That's an important discovery, probably, of a whole new class of worlds that we didn't know about before Clyde Tombaugh.
Pluto and its moon, Charon, are not great spheres of gas like the other outer planets, but frozen balls of rock and ice. Perhaps Pluto isn't a planet at all, but a large piece of icy rubble left over from the construction of the planets all those billions of years ago. It will be decades before humankind ever steps on this dim, distant world. And when we do, we'll need to bring lights. Our sun never burns bright here. We're on a cold, gloomy, remote world. One last sunrise for the album, to complete our solar tour.
Basically, the whole outer solar system beyond the orbit of Pluto is an entirely new frontier. We've been discovering new objects, and there are undoubtedly many more objects out there to discover. Probably not new planets, but smaller bodies, asteroidal things, cometary-like things.
Way beyond Pluto, a third of the way to the nearest star, is the Oort cloud, home of the icy comets. Although far out, they still orbit the Sun.
There's no end in sight in the near future to our discoveries in the solar system.
All the planets, asteroids, comets, and moons add up to just 1,000th of the mass of the solar system. The remaining 999 parts are the Sun.
Here is this huge, enormous body from which spring everything that is life, because life cannot exist without it. And it has this fantastic way of interacting with all the planets around it, keeping them in line. It is like the head of a family, telling the kids what need to be done and providing each of them with what characterizes them and make them different from all the others.
High in the frozen Andes, the Inca pay homage to our nearest star. They call themselves the Children of the Sun, and their midwinter festival of Inti Raymi heralds warmer days to come. The Inca understand the sun's power. We too worship the power of the sun. Electric starshine. All our power was once the sun's. Coal, oil, and gas are solar energy harvested by plants and animals. The sun is our true power plant. But what is this fantastic fireball?
Well, the sun is a star. By and large, it's fairly typical of its class of stars. And it's probably 5 billion years old or something like that. And hopefully will last us another 10 or so.
An island in Big Bear Lake, California. From this oasis of cool tranquility, Professor Zirin studies the hottest, most violent body in our solar system.
We're studying an object that heats the ground and produces rising currents of air. If you look across a hot desert, for example, you can see all the shimmer coming off of the ground, and therefore it is much better to observe across water because water doesn't get very hot, and with this very stable air, we can see things down to about the size of California.
For centuries, we believed this orange furnace was a ball of burning coal. But that isn't the sun's chemistry.
There are processes which are taking the hydrogen, which is the basic building block of the universe, and converting it into helium. What happens is that a helium atom weighs a little bit less than 4 hydrogen atoms. And if you use Einstein's good old formula E equals mc squared, that means if you convert the mass into energy, you get a whole lot of energy for just that little bit of mass.
Its core is 20 million degrees Fahrenheit. Here is atomic ultraviolence. Every second, another 4 million tons of mass is converted into raw energy. Photons, little packets of light, take just 8.5 minutes to travel the 93 million miles to Earth. But their trip out from the heart of the sun to its surface takes an age. Why?
Well, the typical distance that a photon can travel is about this far. And so it goes this way a little bit, and that way a little bit, and that way a little bit, and that way a little bit. And it takes this random walk, which is enormously long. So even though it moves with the speed of light, if you add up the path it travels, since it doesn't know which way to go, it will take about 1 million years.
A prairie fire of hot gas whipped and licked by the rising heat. These aren't flames. There is no oxygen for fire here. This is incandescent gas at 10,000 degrees Fahrenheit. Though strangely, this is the sun's coolest part. The temperature shoots up another 2 million degrees above this in the sun's corona. A crowd gathering to catch a rare glimpse of it. It's India, 1995. The moon's shadow races across them at 1,000 miles an hour. The sun will be totally eclipsed. Darkness in daytime. The lunar disk is just the right size to obscure the sun's brilliant face. This reveals, for 45 precious seconds, the normally invisible corona. A shimmering, pearly white halo. Sometimes, as here, it's drawn out into streamers. These coronal changes reflect the changing nature of the sun's magnetic field. For the sun is far more than just heat and light. A vast magnetic field is generated by the circulation of hot gases within the sun. As the sun rotates, it corkscrews the lines of magnetic force. Harmful cosmic rays stream through space, but they're deflected by the magnetic field. Our sun is a fickle star, flipping its magnetic poles every 22 years. The strength of the field varies, but we still receive some protection. The magnetism is the invisible dictator, influencing every aspect of the sun's behavior. But some solar activity can be seen. A shrine for scientific sun worshippers. The McMath Telescope in Arizona. After 93 million miles of straight-line travel, the light ricochets between mirrors and lenses before being focused on the viewing table. Scientists look at the portents of solar activity, sunspots. They come and go in an 11-year cycle, following changes in the sun's magnetic field. Darker, cooler patches, where a locally strong magnetic field prevents heat from rising. Prominences, huge arching columns of gas, often hang above sunspots, supported by the sun's magnetic field. Hot gases braided by the lines of force. They may reach out hundreds of thousands of miles, spectacular but relatively harmless. Far more serious are solar flares. Sudden, violent releases of stored magnetic energy. They may last only a few minutes, but their power is enormous.
Now, a solar flare is an astonishing thing because you take a region that's just the same temperature as the rest of the sun, about 10,000 degrees Fahrenheit, and you suddenly produce a cloud that's 50 million degrees.
Flares blast vast amounts of particles and radiation into space. The normally steady breeze of electrically charged gas streaming from the sun suddenly becomes a gale of solar wind. At 2 million miles an hour, it slams into the Earth's magnetic field, causing the lights of the aurora. But solar activity has a darker side.
Solar activity affects the Earth and technological systems in many ways. Satellites have anomalies and sometimes fail because of solar activity and energetic particles that come from energetic solar flares. Communications at just about all wavelengths are affected at some time. The radiation hazards are there for astronauts, and for an unprotected astronaut during one of these large solar storms, they can receive a lethal dose of radiation within 2 days.
These are space weathermen looking for magnetic storms, solar flares, and bursts of radiation that are headed our way.
At the Space Environment Center in Boulder, we are the world agency for warnings about solar terrestrial effects. We have a network of observatories around the world. The sun never sets on it. We have a series of satellites that send us data on what the sun's doing and what the environment is in outer space.
Stationed between Earth and the Sun is SOHO, a permanent solar observatory. It monitors the sun's activity. A major peak in 1989 blacked out parts of Canada. Power lines overloaded, and 6 million Quebecers were without electricity.
March 13th, 1989 was a chaotic time for us. People were having system problems, power outage. Of course, the communications were blacked out from satellites that were spinning up for almost 2 days during that event.
The Anik E1 satellite was blacked out. The next bout of activity will come around with the new millennium.
The sun's activity goes through cycles. Sometimes it's very active and sometimes it's quiet. And we think that there's a relationship between this activity and what happens to the Earth's weather system here. Just over 200 years ago, there was a mini ice age, which is related to the time when the sun was very quiet.
A prolonged cold spell, the Maunder minimum, when sunspots were virtually absent and global temperatures fell by about 1 degree Fahrenheit.
It's a little bit like when the sun sneezes, the Earth catches a cold. So what happens on the sun can affect what happens to us here on Earth.
We rely upon our sun's good health. But for everything in this universe, there is a time to die.
When we think about how life has flourished here on Earth, we have to realize this is only really a temporary condition. As we've seen from Hubble, we understand that stars eventually die, and our sun is just another star.
The death of our sun is written in the stars. And through Hubble, we can see stars in their twilight years, trillions of miles away. Gas shooting out, the sign of a dying star. Rings of gas pile up in ripples. This waning star puffs out billions of tons of gas as it expires, creating its own death shroud. Death in the beautiful Cat's Eye Nebula, blowing cosmic bubbles. A small white pinprick of light is all that we see of this dying star. Gigantic clouds form fabulous lobes. Time has almost run out in the hourglass nebulae. These stars will collapse and end their days as white dwarfs. Small, dense stars, about the size of planets. Our sun is destined to follow a similar fate. About 5 billion years from now, it will come to the end of its hydrogen fuel. The goals change to reds as new reactions begin. An expanding vermilion sun, a red giant with hot gases pushing out into space.
So eventually our sun will expand, the Earth will heat up, the oceans will evaporate, life will cease to exist. So our sun will have gone from being the very thing that nurtured life to the thing that kills it in the end.
As the sun expands, so the solar system changes forever. The sun's hot outer layers touch the inner planets. Mercury is consumed. Venus, too. 5 billion years from now, Mars and Earth are all that will remain of the inner solar system. Earth is fast drying up. Moisture-laden clouds have gone. The oceans are disappearing, and the once blue planet will, in a few million years, desiccate. Sunrise over the Earth, 5.25 billion years from now. It's a demon sun. its light shines on what used to be New York City. The oceans have long since vaporized, and now the parched planet shines back the light from a crimson sun. Even the planets hundreds of millions of miles out are ravaged. The atmosphere is stripped from Saturn and blown out into space. The dying sun expels ever more gas at greater and greater speed. Winds traveling hundreds of thousands of miles per hour expand out from the dying sun. In 5.5 billion years, the core of the red giant finally runs out of fuel. Fantastic compression as it falls in on itself. The old sun throws out a last gasp of dust and gas, scattering ashes to the stellar winds. From the storms of destruction, it is sowing seeds for suns that are to be born eons to come. But for the present, the sun will continue to share its warmth and sustain us. And there will be at least another 5 billion years of beautiful sunrises before that final sunset.